Hey, long time no see. Welcome back. It's been a while since we worked on the PDP-12 because we've been working on a cybersecurity education project. But our friend Nick Moffat, friend of the PDP-12, sent us a program to try out. And it's a Hellorld program, which is like Hello World, only missing some letters.
PDP News at 6 o'clock. This is Nick Moffat. Good evening. Texas-based retrocomputing enthusiast Usagi Electric made history in April of this year by running new code on a restored Centurion minicomputer for possibly the first time in over 3 decades. Due to a typographical error, the traditional test output of Hello World was shortened to the unusual greeting Hellorld. Curators around the globe now race to be the first to display the text Hellorld on a variety of antique computer systems. One such effort, for the PDP-12 system, sparked an international debugging effort that linked Britain with Minnesota and Oregon in the United States. Nick Moffat has the story. I've known Dr. Peterson for a long time. I helped him with his first Debian install back in the 90s. Remotely guiding him from San Francisco through shared terminal sessions on his computer in Chicago. Now, I live in London, and I followed this restoration effort with interest. So when I found that Vince Slingstad got the PDP-12 display scope working in his branch of the OpenSimH emulator, I knew I had to use it to remotely guide the machine in Duluth into displaying Hellorld. Here's the program I wrote to do that. The assembled program is 34 12-bit numbers called words. We write them as 4 octal digits, 0 through 7. I've color-coded them based on the role they serve in the program. White numbers represent ordinary PDP-8 instructions. The first digit indicates which instruction it is. The 5 at the front of the first number, 5225, means that that's a jump instruction, causing the computer to run code elsewhere. The last 3 digits tell jump where to go. The yellow numbers represent the data we want to display, with each one representing half a letter. We'll cover that in more detail soon. The cyan numbers are local constants, used for other things. The green numbers are concerned with the switch between PDP-8 mode and link mode. The instruction for displaying characters only exists over on the link side, but I am more familiar with PDP-8 assembler, so I tried to keep them to a tiny critical section. While these numbers are handy for toggling in a short program at the PDP-12 console, let's look at the PAL source code that generated all this. The first several lines of this program are preliminary instructions to the PAL assembler. We give names to some obscure instructions that not all versions of PAL support, and to 2 special memory locations that the link mode treats as ersatz registers. Then, since we've told PAL to place the first instruction at octal memory address 0200, which is 128 in decimal, the numbers at the left show the first actual instruction is the jump we talked about earlier. This will skip over the block of data that we colored yellow and cyan. Now we have all of the character data we want to print. Note that the memory addresses are incrementing by 2 here. That's because it takes 2 12-bit words to print a single 4x6 pixel character. We've joined these 2 words with a semicolon in this file, just to make things clearer. But how do these numbers make up letters? It's not immediately clear. So let's take a look at the most complicated letter, R. That is made from 4477, followed by 3146. This confusing diagram comes from the PDP-12 handbook. It's trying to show us how each of these 12-bit words are split into 2 6-bit pieces. Bits are shifted off of each side, one at a time, from the least significant bit to the most significant. The electron beam zigzags back and forth up the 2x6 rectangle until it has drawn a dot or left a space for each of the 12 bits. This illustration may be easier to follow. Since the left half of the A is the same as the R, which is 4477, we can follow the logic for either. The halves are swapped, so 77 describes the left column and 44 describes the right. Since 7 is binary 111, that means all 6 pixels on the leftmost column are lit. And since 4 is binary 100, we go down the second column, on, off, on, off, off. Now let's take a look at the right half of the R, which is 3146. Tracing down the third column, we see the on, off, off pattern for 4, and then 6 is binary 110. And in the fourth column, binary 011 for 3, and 001 for 1. Many details of computers from this era seem awkward and confusing to us, but this was likely the least expensive way to make the machine work, and most people just copied font data like this from working examples. After all, that's what I did. The code itself is in 3 sections. The first just loads our constants into the named registers that we defined at the start. The green section in the middle does the real work. It switches to link mode and runs its display scope character instruction before switching back to PDP-8 mode. Finally, we have code to display the next character only if we haven't finished the data. We're fortunate that the exclamation mark only uses 1 column of that 4x6 grid, and its second word is 0000. The PDP-8 instruction SNA skips the next instruction unless the accumulator is all zeros. So, we reload the last half CH, and if it's 0, we start over. The phosphors on the PDP-12 scope only last for a fraction of a second, so we need to keep redrawing our text, or it will fade to black. I ran this code in Vince's emulator, and it worked perfectly. So I excitedly sent it along to Dr. Peterson, with instructions to toggle in my 34 numbers, starting at memory address 0200. When he tried it, however...
I'm running your code, and this is what it looks like when I run it. And when I single step it to slow it down, you'll see that the characters are marching across the screen. That's really slow.
Aha! Look at that. So it appears that this code works insofar as it writes Hellorld, but it then seems to keep running through core, drawing whatever bit patterns it happens to find there. It's not stopping at that exclamation mark. Something in the zero detection code appears to have worked in the emulator, but not on actual germanium. This was troubling, as it could indicate a hardware fault in the UMD machine. It's a well-cared-for antique, but you can see other videos in this channel where just resting a hand on the backplane affected the tape drive signals. If this were a program on my laptop, I'd open it in a debugger and set breakpoints and print out values. If this had happened in the OpenSimH emulator, I could have single-stepped the code and logged register and memory values to a file. But those methods are modern versions of something the PDP-12 does in hardware. I begged Dr. Peterson to video the console status lights, single-stepping through one loop as it printed Hellorld. Assuming he'd run out of time to work with the machine in Duluth, I went out for dinner at my local pub here in London. But as we considered dessert, he sent me this.
H, E left, E right, L left, L right, L left, L right, O left, O right, R left, R right.
Double aha. From that brief pause, I noticed a value in the accumulator that I didn't expect to see at all. Right after each character is drawn, it should have been 0. After all, we cleared it at the start of the code. Looking at a printout of the assembly listing, I came up with a workaround. The PDP-8 does not have an instruction to load data into the accumulator from core. Instead, you're expected to clear it and use the 2's complement addition operation, TAD, against that 0. It's a common category of bug in PDP assembler to TAD data into a non-empty accumulator and end up with garbage data. All we needed to do was clear the accumulator after coming back to PDP-8 mode. Then, we'd be adding those zeros from the exclamation mark to an all-zero accumulator instead of the 0030 that we were left with. I figured this would work whether the bug was in the hardware or in the emulator. But was there a fault in the machine? I posted a summary of the situation to the Vintage Computer Federation forum. Vince Slingstad, who wrote the emulator, tested the code on his own hardware in Oregon. Sure enough, his system matched the UMD behavior, always returning from the DSC instruction with 0030 in the accumulator. This suggested the problem was in the emulator, but why? The answer came from a manual for the original Link computer. They documented right there on the page that DSC leaves a 30 octal in the 5 least significant bits of the accumulator. It was quite a relief to find out that the hardware wasn't broken. Vince put out a fix for the emulator, and I used it to test my workaround, which is now confirmed to be the correct fix for this. All that was left was to try the new Hellorld on the UMD machine.
Okay, now let's try it. So, with any luck, we'll have Hellorld. Aha! Success! Oops. There it is. Oh, and you can see Kyle in the background. Wave to the camera, Kyle.
Hellorld to you too, Kyle.
So there's Hellorld in the flesh. All right. Well, Nick, you did it. And thanks for sending us the code. And thanks to Usagi Electric for this sort of fun challenge. And because of it, we fixed a bug in the PDP-12 emulator and at least confirmed that our machine can run this code. So I hope you enjoyed this, and thank you so much.
Nick Moffat, PDP News, London.